Stachura, who will tell us about Snell's law in liquid crystal objects.
Thank you, Argir. And thanks to the organizers for the chance to talk to you today, and thanks to all of you for making it to the last day in the morning. So I'm coming from Atlanta, Georgia in US, and now that the jet lag has remedied, now it's time to go back home. Right? Okay, so today I want to tell a story about optics. So my background is a little bit different. I'm coming from electromagnetic theory and optics background. So I want to tell a story about optics today, especially geometric optics, and I'll talk about some very classical principles, but perhaps applied in newer settings. So I want to talk about geometric optics of quite general materials. I'll try and keep this general and talk about anisotropic media in general. And today when I talk about anisotropy, I'm going to mean electromagnetic anisotropy. So I'll talk about Fermat's principle, and I'll give a variational perspective on Snell's law, which is a very classical law of how light propagates between two materials. And then I'll end with some very recent work on new materials, which are these temporally modulated materials or time-varying media, and see what a version of Snell's law looks like in this case. And then I'll end with some challenges, and in fact I could actually probably spend the entire time on just challenges itself, but I'll just end with a few of the challenges in this area. So I'll start with some quite basic things in electromagnetism. So we'll start with Maxwell's equations. So we have four fields. We have E and H, which are the electric and magnetic fields, varying in space and time, and we'll say in 3D. Then we have the two other fields, D and B, the flux density and magnetic induction vector, and then we have two densities, the charge density and the current density. Here, bold vector X is living in R3 and T is positive. So I'm going to go from Maxwell equations to geometric optics regime, and what does that look like? Well, first, before we go to the geometric optics regime, I actually have four fields, but typically when you have these four fields, you need to have some kind of relations between these four fields. These are called the classical constitutive relations. And they typically look something like the following. So coupled with your Maxwell system, you have relationships between the D field and E and H, and the B field, depending on E and H as well. And so this leads to some general relationship of the form that D and B is proportional to E and H, possibly by some matrix that looks like this. Okay, and just some basic definitions. We will call a material isotropic if the diagonal parameters epsilon and mu are scalar multiples of the identity matrices. So each of these, I should mention, could be 3 by 3 matrices. So if these parameters epsilon and mu are scalar multiples of the identity, and the off-diagonal elements are 0, then we'll call the material isotropic. And if at least one of the diagonal elements epsilon and mu is not the scalar multiple of the identity, and the off-diagonals are 0, then we'll call the material anisotropic. Okay, you could also have everything non-zero and being a 3 by 3 matrix. Those are bi-anisotropic materials. We won't talk about that today. So what I'll focus on are these anisotropic materials where epsilon and mu, these so-called classical material parameters, are typically 3 by 3 matrices. So how do we get to geometric optics? This is what I wanted to focus on today. So starting from Maxwell, we make a plane wave ansatz to the Maxwell equations in terms of the following forms. So we guess that the E and H fields take the form of some amplitudes E tilde H tilde, and then we have the iconal function, the classical iconal function, which we denote by, psi. We have K0 as this wave number of vacuum, and omega is going to be the frequency of oscillation. And what does the geometric optics limit correspond to? This means I'm taking large values of K0 or equivalently small wavelengths, and this can be mathematically translated to a requirement on the divergence of epsilon and E in terms of the wave number K0. So now I want to leave Maxwell and just focus on the geometric optics regime and see what we can say in this setting. One of the key players for optics is going to be the index of refraction of a material, and classically this is a property which describes how fast light is propagating in a material. You can define it naively as the ratio of the speed of light in vacuum to the speed of light in the material. And what we're going to use today for electromagnetic radiation, we could write the refractive index as the square root of epsilon and mu, where epsilon is called this material permittivity and mu is the permeability. So it's the same epsilon and mu that we saw in the previous slides where they were coming in the constitutive relations relating the four fields to each other. Okay, so I like this slide because even today I'm still surprised myself on how useful optics is and how many wonderful applications there are out there. So the ray optics, what I'll talk about today, is a good model if your wavelength of light is much smaller, for example, than the distance that the light is traveling. And so I just list a couple of interesting examples here. There are many, many more, but just a couple that come to mind. So the first one where you can use this model is, for example, uncoupled wireless power transfer. So you want to transfer power from one place to another wirelessly somehow, and one model for this is basically you take a collection of light rays between a transmitter and a receiver, and you can use geometric optics to study this problem. There's also this very nice paper in, I believe it was PRX, from Dr. Smaliuk and his collaborators, who looked at optical interactions with topological solitons. We heard a lot about these yesterday with skyrmions, and so they were looking at how does light interact with, for example, baby skyrmions. Another soft matter application I saw recently was using optics ideas, was trying to model the optimal buckling of some tissue, such as a plant leaf. And this was quite interesting. He was using ideas and techniques from geometric optics, such as the classical iconal equation and the Fermat principle that I will talk about today. And then more along what I've looked at things in the past, you can introduce abrupt phase changes over the scale of the wavelength of light being used to manipulate light via these things called metasurfaces, and these are things I've looked at in the past. So somehow, if you've heard of metamaterials, can be seen as somehow two-dimensional versions of these metamaterials.
So Eric, these are skyrmions in magnetic materials or in a different medium?
I don't think these were magnetic materials, yeah. Okay, so these are just a couple of many, many applications, so it's nice to motivate why geometric optics is still useful today. Okay, so I wanted to start quite basic, so let me talk about a few types of anisotropy. So I can typically write my permittivity for an anisotropic material in the following way, and this will possibly depend on space and with respect to the standard basis in 3 dimensions. But we can diagonalize this matrix and write it in the following form. And then we can distinguish between 2 types of anisotropy. So when 2 elements of the diagonal are equal, we will call this material uniaxially anisotropic. And if all 3 elements of this diagonalized matrix are distinct, then we'll call it biaxially anisotropic. So for the time being, I will focus on uniaxial anisotropy, but I will give you a formula for biaxially anisotropic materials later. Okay, so this is fairly well-known stuff. We've seen the director a few times this week. So just one thing I want to point out, I use D for the director field instead of N, because N for me is refractive index, so D is going to be this unit vector field here. And you can write this permittivity epsilon in terms of this director field D, and as well as in terms of these so-called extraordinary and ordinary refractive indices of the material. And the extraordinary...
Eric, now you are jumping directly to nematics?
Not necessarily, yes. So you can still define this optical axis quite generally, and then this will be when you focus on liquid crystals, this will be the standard director. Okay, so the permittivity can be written in terms of D, in terms of these refractive indices. So the ordinary refractive index will define as the square root of what we call epsilon perp, where this is the permittivity in the direction perpendicular to D, and E, the extraordinary refractive index, will be the square root of epsilon parallel, which is the part of epsilon that's going to be in the direction of D. Okay, so one of the interesting things we see when you look at anisotropic materials that you don't see when you study classical physics in university, for example, is how do you even define a light ray? You have to be a little bit more precise than you usually are in your college level physics class. Okay, so you can relate the displacement field D to the electric field in terms of these refractive indices NE and O and this director D. So the formula itself at the moment is not so important, but the thing to point out and recognize is that D and the electric field are not necessarily parallel here. Whereas for isotropic media, they are parallel, which can be seen easily through this classical constitutive relationship that D is proportional to the electric field, maybe by some constant epsilon here. But okay, so I meant it's not necessarily clear. We have to be clear on how we define a light ray before we can even do optics. So let me spend a few minutes discussing what does that actually mean. Okay, so let's talk about simpler materials, isotropic materials. Then we can define light rays as integral curves of the wave normal p. So in particular, you can understand a light ray as the trajectory of a vector, which is orthogonal to a particular wavefront. So this is a very classical definition. This is, you can be found in the old book of Born and Wolf, very classical things. Fine. But when you go to anisotropic media, you have another direction that is of interest, and that is introduces the so-called pointing vector. The pointing vector for the electromagnetic field is just classically defined as the cross product of the E and H fields and represents the flow of energy. And so it's a classical calculation how you find the time average of the pointing vector. And so another thing you can define is you can define a light ray as an integral curve of this time average pointing vector. So you don't see this in classical physics and isotropic media because these two directions are parallel. But in general, for anisotropic materials, these could be different directions because the electric field E and the displacement field D, they are typically not parallel, as we saw in the previous slide. So there are two different directions. So before you even start to do optics, you have to be a little bit careful and say how you are defining a light ray, which is the direction that you are particularly interested in. Okay, so now we can start to get towards liquid crystals a little bit. These are what we know are birefringent materials. So what is happening in a birefringent material? You have an incident light ray. So this is the type of situation that I'm going to be interested in today. You have an incident light ray upon some kind of material. Then I want to see how the light is propagating in the second material. This is Snell's law, basically. Okay, so when you have a birefringent material, we know that the incident ray is going to split into two rays. You have an ordinary ray and an extraordinary ray. Mostly what I'll be interested in is the extraordinary ray. And one thing I'll point out, and we'll see in the coming minutes and slides, is this slide is a bit misleading. It makes one think that maybe the light rays are actually linear trajectories in the second material, which is generally not the case. We'll see why this is true later on. But the point is that we're going to typically split into two rays once we strike a birefringent material like this. Okay, and I think we've seen this before, that when you look at the extraordinary ray, it feels an effective refractive index, which depends on both refractive indices NE, the extraordinary refractive index, and NO, the ordinary refractive index. This is a very classical calculation which can be found from the Eikonal equation and derived via this so-called optical indicatrix. Okay, I just include the part for the extraordinary rays. You have a corresponding part for the ordinary ray as well. And how do you actually find the effective refractive index? It's a straightforward calculation. You can decompose the wave normal vector in terms of its magnitude and direction in this way, and then this way you can plug this into your optical indicatrix, and quite quickly you can get the effective refractive index. So this is in the uniaxial case. I'll show you what it looks like in the biaxial case later on, but it's a pretty straightforward way to get the effective refractive index in terms of these refractive indices NE, NO, and this director D. Okay, great. So now let's move to Fermat's principle. These are classical things, and then I'll get to the Snell's law in a few minutes. So the correct notion of length here is not regular length, but is the so-called optical path length, which we can define now. So if you take a path in R3, so we say that the optical length of a path taken by a light ray traveling from some point A to some point B is defined to be the integral of the refractive index along that path. Okay, so if you have a constant refractive index, then your optical path length is really just a multiple of standard length, so this is straightforward, but in general it's not going to be like this, especially when you have more sophisticated materials. Okay, so Fermat's principle can be formulated then in the context of calculus of variation, saying that basically the variation of the optical path length is going to be 0. So we look at the optical path length function, we'll take variation, this should be equal to 0. So I want to do a quick calculation which is quite illustrative and seeing what variation of this looks like. We'll look at the Euler-Lagrange system, and then we'll get a very famous equation for the light rays and spend some time looking at what this actually means. Okay, so let's just do a quick calculation that can be done in your calculus class. So we can write our optical path length in terms of the arc length of a curve, where we write r of t in terms of x, y, z of t. Then we can write arc length explicitly. And so it's a very straightforward calculation. You can take variation here, and this is going to lead you to your system of equations. The Euler-Lagrange equations, you get 3 of them, but I will condense them and write them as this way. So you get d by ds of the refractive index evaluated along the curve, dr ds, is equal to the gradient of the refractive index evaluated along the curve. And this is sometimes known as the equation of the light rays. So this is a very nice equation, and from here, this is what I always tell my students, you can from here quickly see that the trajectory of a light ray in simple isotropic materials are going to be a straight line. So we can see this very quickly, right? So if n is constant, you can pull this out. So you get r double prime. If n is constant, the gradient is 0. So you get r double prime is equal to 0. So you're going to get a straight line for the trajectory. Very straightforward. Okay, but if your refractive index is not constant and you have some spatially varying refractive index, this becomes a much more challenging and yet much more interesting problem. And so if n is constant, then we see this as straight lines. But I also wanted to bring up the following. This comes up quite often when you're studying so-called gradient index optics. Okay, you have a gradient here. What they call sometimes grin optics or grin lenses. This is not necessarily new. There is a very classical lens called the Lundberg lens and related lens called Maxwell fisheye, where, for example, if maybe you say that your refractive index is radial, maybe you can say something more about this equation. Maybe you can say something about the solutions of this. So one of the classical ones is called the Lundberg lens, and the radial refractive index is taken to be this something that looks like this, where capital R is the radius of the lens that you have. With such a refractive index, then you can actually say something with quite a bit of work, though. You can actually say something about trajectories of the rays going through a Lundberg lens, and it turns out in this case, for the Lundberg lens, that you get the rays trace out paths of an ellipse. And I think we saw a few days ago that someone mentioned special functions coming up in optics, and this is one of the cases where special functions come up, because solutions of this will involve some hypergeometric functions, and from the properties of hypergeometric functions, you can see that your solution will trace out an arc of an ellipse. So this equation comes up quite often in gradient index optics, and the applications of this are actually quite nice, and I include a few of them. They include optical data storage, solid-state lasers, and imaging applications, of course, in particular for microscopy. So they're very interesting things. The problem is, okay, yes, this is an ODE, but it can be quite a complicated ODE. Okay, so yes, when you go to more complicated materials such as liquid crystals, this becomes much more complicated. But let me show you a quick calculation of something that you can actually do. Okay, so let's go to a liquid crystal example. Suppose we have a hedgehog in 2D. I can write my director field that looks something like this in a uniaxial pneumatic. And then in this case, I'm going to start to relate some geometry actually in here. There's very interesting geometry going on. So I can write the length of a curve in space in arbitrary coordinates, supposing that I have some metric tensor, which I'll call G. Then you can compute the length of the curve between 2 points A and B in some coordinate system by integrating the element ds along that curve. So you have this very nice formula for S in terms of the metric G. Okay, I'll get back to the hedgehog example in a second, but let's see. So this can be for a general coordinate system. Let's try and apply this to Fermat's principle and see what this gives. Well, this is classical calculus of variations again. So I'm going to take my functional to be my optical path length functional, which is the integral of my refractive index. And I'll take a general line element with metric G. Then, okay, calculus of variations, you get the Euler-Lagrange equation, you get classical geodesic equations with the Christoffel symbols in terms of the metric G. So the interesting thing here is, okay, if I put this in the context of liquid crystals or anisotropic media in general, that you can, okay, for smooth directors D, we can understand light rays as tracing out geodesics in a certain geometry, which is very interesting. So let's now go back to the previous example when I had shown you the 2D hedgehog and see that you can actually do this out quite explicitly. Yeah, actually this is quite straightforward. In 2D, you can get the geodesic equations for this 2D hedgehog, and you get this pair of second order equations for okay, it's slightly easier in polar coordinates for r and theta. Okay, it's not linear, but actually it's not bad. It's doable by hand, and I'll just put the formula. You don't have to look too carefully at it. The point is you can actually get something very concretely by hand, a solution for this problem exactly, in terms of a number of integration constants. Okay, so that's something that can be done explicitly. And one of the interesting things relating to this is you get some interesting, so I'm coming from optics and imaging background, so I was quite interested in seeing these results, which are coming from maybe some 15 years ago. You get some bending of light rays in a particular direction. Okay, so here we see that there is a diverging lens behavior on the rays for this particular defect. And this, again, this has been observed some 15 years ago or something like this. And not only do you get diverging behavior, you can also get converging lens behavior, but this will depend on the disclination that you have. So you can get both diverging and converging lens. What do I mean by this? So here we see the rays are kind of diverging away from the origin, but you can also, depending on the disclination that you can also have rays that are going to be bending and focusing towards the origin as well. So this was a very interesting phenomenon coming from the geodesic equations, and again, was observed some 15 years ago or so. Okay, so finally I've gotten to the main idea of the talk, which is Snell's law. Okay, so I'll set this up generally. I'll go through the classical versions of Snell's law and how we understand it and how we use it, and then I will generalize to more sophisticated materials. But right now, let's keep things quite simple. Suppose you have a surface in 3D, keep it general, that separates two particular materials. And in the simplest possible case, suppose they're homogeneous and isotropic materials. Air and glass or something very simple. And they have some refractive indices n1 and n2. So how can I formulate Snell's law? It turns out for the applications which I'll talk about at the end, it's quite useful for us to have a vector form of Snell's law, which is not something maybe you usually see in your college physics class, so I wanted to mention this here. So how can we formulate the vector formulation of Snell's law? It goes as the following. Suppose you have a light ray having some unit direction x in the sphere. So x is your incident ray. And it travels through your first material, and it strikes your surface at some point. And the Snell's law says that this ray is refracted into a unit direction m, according to the following formula. So the refractive index times the cross product of the incident ray vector with the normal vector pointing from the first material to the second is equal to the second refractive index of the second material times the cross product of the refracted direction cross product the same unit vector. So you get a lot of information from this vector form, which may be strange to see at first, but you recover a lot of information and a lot of classical things from this vector formulation. So let me talk about a few of the things that we can learn from this vector formulation. So in particular, you have the three vectors, the incident ray x, the refracted ray m, and the unit vector nu. These are all on the same plane. This is called the plane of incidence. So maybe you've seen the more familiar scalar version of this law, which, okay, comes from this because you can just take norm on both sides and we have unit vectors. So taking norm gives you the scalar version of Snell's law. So the classical n1 sine theta 1 is n2 sine theta 2. And just to be precise here, so theta 1 is going to denote the angle between the incident ray and the normal, and theta 2 is going to be the angle between the refracted ray and the normal. So this is perhaps the more familiar Snell's law that you've seen in college physics class, but it comes directly from the vector form as well. So it turns out one useful thing for us to do is write the vector form. So let's go back and see what the vector form says. So is that n1, the cross product of x with nu, is equal to n2, the cross product of m with nu. Well, I can rewrite this in the following way. I can rewrite that as n1x minus n2m. All of that cross product, the vector nu, is 0. So in particular, vector calculus means that this vector has to be parallel to the normal vector. And so another way that we typically write this Snell's law, so if we look at kappa to be the ratio of the refractive indices, then we can write the vector Snell's law in the following way. So it's the incident ray minus the ratio of the refractive indices times the refractive ray is a constant, which we call lambda, proportional to the normal. And this formulation is particularly useful. Like I said, I'll talk at the end about the applications, in particular for the design of lenses and other things like this. So there are reasons for wanting to write it like in this particular way. And yes, we get some constant lambda here, but from the geometry of the problem, we can compute this constant explicitly. It will depend on x, it will depend on n, but it can be found extremely explicitly. So we know what lambda is. And in fact, I should say, this isn't just the classical materials. As I said, I come from somehow more metamaterial background. So if you give me the fact that if there is a way that you can understand N2 being negative, which there is, these are so-called negative refractive index materials, then you can do something similar, even if N2 is negative here. Okay, so Snell's law is going to look something like this, and we're interested in vector formulations of Snell's law for, as I said, I'll mention at the end, typical lens design type problems. But now we want to make the materials more sophisticated, right? So all of this was just for classical materials, air and glass, water and glass, something simple. Now I want to try and introduce some anisotropy or inhomogeneity and see if I can do something similar. Okay, so in some recent work with Christian Gutierrez, we consider a variational perspective on this. And now what I want to introduce is a phase discontinuity and see what I can say. So we're going to look at classical version of what they call the Weierstrass-Erdmann corner conditions in the calculus of variations. And I'm going to introduce a phase discontinuity. So I'll talk about the mathematics of this, but I'll also talk about physically in different contexts and what this means in the context of metamaterials or metasurfaces, but also in the context of liquid crystals, what this phase would actually represent. So I want to include a phase discontinuity. So let me draw a picture now. And the setup is quite simple to visualize. So, okay, we do this in Rn, but we imagine mainly n equals 2 or n equals 3. So you take some domain omega. And then you have some smooth hypersurface which divides my region into two connected and closed domains. We'll call them omega 1 and omega 2. Such that you have basically the following picture. Okay, we can do, like I said, we can do this in n dimensions, but imagine n equals 2 or n equals 3 for applications, basically. So, in addition, I have two functions. I'll call them f1. So f1 is defined on the left part on omega 1 and on Rn minus 0. And I have another function f2 defined on the other region omega 2 cross Rn cross 0. So I need these to be C2 functions, and I need them to be positively homogeneous of degree 1 in the second variable. Okay, so I have f1 on the left, f2 on the right. So I have f1 here, and f2 over here. These are given. Sufficiently smooth functions. Okay, there are some more precise technical details that I need, but for the most part, this is basically what we need to start. And now I'm going to define my function f defined on the whole region omega. Again, depending on two variables, the second variable will not be a 0, defined in the following way. So I'm going to define f to be f1 if my x is belonging to this first region omega 1. And then I'm going to define my f to be f2 if my x is belonging to the second region, omega 2. So in particular, what's going on here is we have a function that may be discontinuous along this hypersurface dividing these two materials. All right, so we're going to be given let's say, some time interval S1, S2. We're going to consider a class of admissible curves, which are continuous, but not necessarily differentiable at some time S0. So we imagine that this time S0 is, if you can imagine that you're going to have rays going from one region to the other. Maybe you have some light rays going like this. The time S0 is going to correspond to where you're striking this hypersurface which divides these two materials. So the curves will be continuous, but not necessarily differentiable as some particular value of s, which we'll call S0. Okay, so given such a curve in this admissible class of curves, I want to consider now the following functional script f, which is going to be defined in the following way. So from time s1 to s0, so that means I'm going to basically be in this region in omega 1. So I want to look at the integral of this function f1. From s0 to s2, that means I'm basically going to be in the second region, so I'm going to look at the integral of f2. But now again, I'm introducing this phase function. So what is this phase function? So psi is going to be at least a C1 function, which is going to be defined in some small neighborhood of this surface. So psi will be defined in some small neighborhood of this surface. And the last term of our functional is going to be psi evaluated at x of s0, so this is basically this crossing point here. And this is the functional that I'm going to look at. Okay, so mathematically this is what I have. This is basically a C1 function defined in a small neighborhood of the boundary, or sorry, not the boundary, of the surface. When I give applications of the result, I'll tell you what the psi physically would correspond to. All right, so we're going to suppose the minimum of my functional is attained at some curve, x, in this admissible class of functions. And given a parameter epsilon sufficiently small, it's a bit tedious, but we can construct some curve xi depending on s and this parameter epsilon, such that basically this function xi is the union of extremals on either side of my surface on my interface. One thing I want to point out is I'm fixing the endpoints S1 and S2, so maybe this is my S1 and correspond to S2, so I'm fixing my endpoints so that these extremals that I'm gluing together are somehow starting and ending at the same point as x. So as a function of this parameter epsilon, my functional f has a minimum, so basically the variation is equal to 0. So if we crank this out, basically this leads us to the following system of equations. Let me just describe some of the notation here. So subscript x means gradient basically in the first variable, right? Because f and all these f's were functions of two variables. And subscript v basically is gradient in the second variable. So we have all of this on the left-hand side for s less than s0, and then we have the corresponding system for s to the right, bigger than s0. So if we unpack all of the properties of this function xi, which I didn't write out explicitly, but if we unpack all of the properties of this function xi, which we constructed, then all of this together means that we have the following. It means that if I look at now the velocity gradient, I'll call, of f1, now let me explain some notation. So x of s0, here this is the curve evaluated as s0, my crossing point. X dot at S0, right, we're assuming that this may jump, so this only has a one-sided limit. So since I'm looking at F1, my one-sided limit is approaching from the left. So this is X dot, and the limit as S goes to S0 from the left of X dot. And similarly here, my one-sided limit, I only have a one-sided limit. Now, since I'm looking at F2, I'm coming from the right, so my one-sided limit is from the right. And so this quantity, all of this, plus my phase at x of s0, which is well defined by construction of psi, all of that together, dot product with w is going to be 0, and this is going to be true for any vector w, which is orthogonal to the normal vector to the surface at x of s0. Sorry, this should be x of s0. And so, unpacking a little bit more, we get what we call this generalized Snell's law of refraction, which may not actually look like a Snell's law, but I will give you some examples in a few seconds to illustrate it. So we get that this velocity gradient evaluated here with this one-sided limit from the left for x dot, minus the velocity gradient of f2 with the other one-sided limit for x dot, plus the spatial gradient of this phase psi evaluated at this crossing is proportional to the normal vector at this crossing point. So this is what we call this generalized law of refraction. Which includes this phase discontinuity. And again, it's not clear that this is a law of refraction, right? Because I just have functions f1 and f2, but I will specify how you can actually get problems related to optics in a few minutes. Okay, so this was refraction because I have one ray starting in here going to the second material. We can do a similar setup for reflection as well, right? So you can do that, but you have to change things a little bit because your first ray will strike the surface and then it's going to go back to the first material. The setup is going to be similar, but you have to tweak a little bit the admissible class of functions, but we can do something similar for reflection as well. Okay, so now let's actually see how this might be a Snell's law. So let me give an example of how we recover our old result for metasurfaces. Basically the idea is you take these f's to be proportional to the refractive index of your material. So n1 and n2 are going to be, in this case, we imagine psi for this metasurface is this abrupt phase shift introduced at the interface of two materials. And f1 and f2 are just going to be proportional to the refractive indices of the two materials on either side. And if you plug this into the formula that we get, we basically get a vector form of Snell's law. And if there was no phase discontinuity present, this is exactly the standard vector form of Snell's law that I showed you a few slides ago. So this is the similar thing. And the idea here is we just take these functions f to be proportional to the magnitude of the velocity and times the refractive index. Okay, and because so we also have some results for liquid crystals now by looking at the interface of the uniaxial and even biaxial pneumatic liquid crystal. I didn't write out the formulas because it would take up the whole slide and it's not particularly meaningful to look at these whole things, but again, we can take these functions f to be, if you want, the effective refractive index for the extraordinary ray. Now the interesting thing here is what is this function psi? So in the metasurface context, this function psi corresponded to this artificial abrupt phase shift that was introduced. Now psi, in a liquid crystal context, is going to be related to this so-called Pancharathnam-Berry phase. And this is basically the phase which is acquired by light after it passes through a birefringent material, such as a liquid crystal. So this is quite interesting, and from the optics and engineering perspective, these PB optical phase elements for imaging are quite useful. They're practical, they're relatively cheap, and they're very tunable, so it's quite nice to introduce these PB phase optical elements for imaging applications. Okay, running a bit short on time then. So I gave a formula here for the effective refractive index for biaxial materials. Is just nothing to look at here. It's just quite complicated, but the point is you can get formulas even for the biaxial case. It's tedious, but one can do it. So let me end by talking about some recent work in temporal materials. And these are really quite interesting materials by using time, essentially, to gain additional control of electromagnetic waves. So the applications include temporal modulations of metamaterials, or if you want 2D metasurfaces, which can be used via liquid crystals. You can imagine a slab of pneumatic liquid crystals patterned on the micron scale. And what we do for these temporal materials is provide a rigorous analysis of Snell's law at a temporal interface. So all of this was for spatial interface, but now we can think about interfaces in time, which is quite interesting. And this occurs when a material parameter is changed rapidly while the optical wave is present. And one way this is obtained is through a strong optical nonlinearity, so order 3 basically. And you can use an ultra-fast femtosecond order laser pulse to do this. So the picture is the following. Now you have an interface in time rather than an interface in space. And the question is, how does light propagate through these interfaces in time? So it's quite different, and I'm not going to be able to explain everything in just a few minutes, but it's quite interesting. You can get analogs of the classical spatial reflection and refraction, except what does reflection mean? And the answer is the reflection is not how you might think of it. It's not reflecting backwards in time in the sense of propagating in the past. So this is quite a tricky thing, but what we see is actually this reflected wave, in giant quotation marks, reflected wave is going to correspond to having a different frequency. So one of the, maybe I'll skip the precise assumptions on the material parameters. One of the interesting things for these objects is that classically across spatial interfaces, frequency is conserved. Now wave vector is conserved across temporal interfaces. So you actually have new frequencies being generated across temporal interfaces, which is very, very interesting. And the point is we can get a version of Snell's law, and this is what the Snell's law looks like across temporal interfaces as well, for quite general material parameters, actually. And so here you have the N2 and N1, which is the classical Snell's law, and KT and the KI are the incident directions, basically, and the transmitted and reflected directions. So you notice you have omega 2 and omega 3. So you have different frequencies being generated at a temporal interface. Okay, so let me end just with some challenges. Like I said, I could have spent the whole time just talking about challenges. One of the things we're interested in is calculating precisely and quantitatively Fresnel formulas, in the sense of wanting to understand precisely how much energy is transmitted or lost due to reflection, for example, at an interface of a nematic or a cholesteric. The challenge is when you have such a surface and a phase discontinuity, even if you have a plane wave striking your interface, then the transmitted wave, whatever that may mean, is not necessarily a plane wave. You're going to have general quasi-plane wave. So this produces mathematical difficulties because you actually have to compute the magnetic field, which is quite difficult. So I don't have much time, but let me just say, lens design, these are typical things we've looked at in the past, so we're quite curious as to what can be done now. So what do I mean by this? So I mean, you give me a first surface of a lens, then I will construct the second surface of a lens such that the material sandwiched between them will do some particular imaging application that you want. And the idea is the second surface is constructed in such a way to correct for any optical aberrations that are introduced from the first surface. So we've done this a bit for linear trajectories for isotropic media, but I'm quite curious to see what can be done when you have more nonlinear trajectories. Can you do some similar lens design problems? And if you're interested in more theoretical PDEs, there's this very nice connection to optimal mass transport and nonlinear PDEs of Monge-Ampere type, which look like the determinant of the Hessian of U, plus some nonlinear function of U in the gradient is equal to some nonlinear function of U in the gradient. This is all related to this lens design and optimal mass transport framework. And all of this has been looked at previously in the context for linear trajectories for isotropic materials. Basically, if you look at surfaces of uniform reflection or refraction, then the defining function of these surfaces will satisfy some nonlinear PDE of Monge-Ampere type. And if you're interested in PDE theory, you can go through this whole Holder or Sobolev regularity theory of nonlinear PDEs of Monge-Ampere type. People like Caffarelli and collaborators have looked at things like this in the past. But in the context of optics, this has just been for linear trajectories. The question is, what would happen? Can we do something similar for nonlinear trajectories in anisotropic materials and things like this? So this is quite an interesting question, but I imagine quite difficult. Okay, I think with that, I'm just about out of time, so I want to thank you for your attention.
Yes. Sorry.
Well,
Carmen.
yeah, okay. Thank you for this beautiful talk. So I wanted to ask you what effects would play, what kind of role would, say, a point effect would play in this picture? And then second, do you have any intuition of why, say, experiments show that if you shine light in a liquid crystal with the defect loop is going to keep cycling around the loop?
This is a good question. So I erased this point from the slide because defects are quite challenging to handle mathematically. So I guess in the context of the spatial law of reflection you were talking about, right? When we talk about light going between two materials.
Would this point zero that you picked up could actually be a location of the defect?
Say that again?
The point zero that you pick up could actually be the location of the defect?
It's an interesting thought. We haven't thought about this. We've thought just about thinking of this as really an interface, but I wonder if maybe you can think of this as somehow maybe including a core or something and a defect there. This might be a way to incorporate defects here. It's quite interesting. We haven't thought about this though, but that might be a way to approach this. Because we need some kind of smoothness or regularity of our functions to do the analysis here, but okay, if you have defects and you're not looking at Q-tensor, then you need only like H1, but this causes a little bit of difficulties when you're talking about the ray optics, unfortunately.
Yeah.
So, I don't know what the derivation of Fermat's principle is from wave optics, but it's a stationarity principle. Now, sometime during your talk, you slipped into talking about minimizers. Now, and you used the Weierstrass-Erdmann corner conditions. Now, of course, that may not be a problem in the sense that you had some sort of stationarity conditions, but for the Weierstrass-Erdmann corner conditions, you have to take inner variations. So it seems to me to be a question of how you derive Fermat's principle from wave optics will handle that kind of variation.
Right, yes, good point. So I kind of glanced over it though. So we go through this careful analysis where we look at the inner variations, and it's a version of the Weierstrass-Erdmann corner conditions. It's not quite the classical ones.
Yeah, but the question is, but Fermat's principle, does that, I mean, the derivation of that from wave optics, does that cover that kind of inner variation?
That's a good question. So there are many versions of, there is a version of Fermat's principle. I think it's called Fermat-Grandjean principle, which handles this anisotropic case.
Can you incorporate the backcoupling as well, so that the vector field adapts to the rays, or is it like?
Can you incorporate what, sorry?
The backcoupling, so that the vector field adapts to the rays, or it's too hard.
It may be possible, I don't know, but we were just trying to do the simplest possible thing that we could actually do, and this was still quite difficult. Yeah.
Okay. So